Welcome back to this deep learning playlist. Please consider subscribing to the channel if you are new here and consider watching all the tutorials in sequence to have a better grip on the subject. In this lecture, we will be discussing about forward and backward propagation within a deep learning neural network. And before we go ahead and cover this topic, there are few prerequisites that you should be absolutely clear with. First is linear regression. Second is a knowledge around all types of loss functions. And third would be a basic understanding around gradient descent. In case you need clarity with any of these topics, then you will be able to find them within the machine learning playlist that we have covered recently within this channel. I will provide you the link below in the description box. Please do consider checking them out. And in case you are already done with these topics, then let's go ahead and get started with today's lecture. Let's try to understand in a nutshell that what is the overall meaning of forward and backward propagation within a deep learning neural network. Let's talk about forward propagation first. So forward propagation is a journey where we get started by providing the input values of the features to the neural network along with the coefficients, or you can say weights, down to the chain so that we can have a prediction value, and then we calculate the loss. And when we are talking about backward propagation, it is a reverse journey in order to reduce this loss by adjusting the values of these coefficients. And this entire process is actually called the training of a model or training of your parameters, these parameters. So in case you are being asked in your interview that what do you understand by the meaning of training of a model, then as a simple explanation, you can say that training of a model means adjusting the values of these weights in such a way that we achieve the minimum loss, which means our predictions become very closer to the actual values. Now, since we have a basic understanding around what is the purpose of the forward and backward propagation, in the rest of the entire lecture, we are going to break down this entire process in details and we will understand this to the root level. So as you can see, we have two input features, which is X and Y, and the journey starts from here. We pass the value of the feature X to the perceptron P1 and P2 with these two respective coefficients, which is A1 and A2. So value of X multiplied by A1 goes to P1 perceptron, and value of X multiplied by this weight A2 goes to the P2 perceptron. And similarly, the value of feature Y gets fed into the P1 and P2 perceptron with these two weights respectively. So when we are saying weights or coefficients, what we actually mean is the value or importance that we are providing to this particular feature in order to do the prediction here. So let's say, for example, we have only one perceptron, perceptron P, and we have two features X and Y, and their respective weights being A and B. And let's say the value of A is 0.3 and the value of B is 0.7. And we are doing the prediction by this linear equation, which is X A plus Y B plus, let's say we have a bias C. So this is the linear prediction that we have, which gives us the output Y hat, the predicted value. So over here, this particular example is telling us that the feature X or the value from feature X has 30% importance towards the prediction, and the other feature Y has 70% importance, or you can say contribution, towards making the prediction Y hat. So these weights or coefficients decides that how much importance or say a particular feature has towards making the prediction. And let's say, for example, we are initiating these weights by 0.5 here and 0.5 here. In that case, of course, this predicted value will give us a higher loss that we will try to reduce further. And in order to get this loss reduced, the model will try to train itself in such a way that it converges the values of these coefficients as these values. So I provided this entire explanation just to give you some clarity around weights or coefficients. Because to be honest with you, in my initial days when I was studying machine learning or deep learning, at that time I used to be very confused with terms like weights or coefficients, and I was not able to understand the meaning of it. Later on, I realized that weights or coefficients are nothing but kind of a measure that gives you some understanding that how much importance a feature has or how much say a feature has towards making the prediction. Okay, now back to the topic. So after feeding the value of feature X and feature Y with these four coefficients respectively, the linear equation on P1 perceptron becomes this, where C1 is the bias, and the equation on P2 perceptron becomes this, where I have kept C2 as the bias. And then these values of Z1 and Z2 becomes the input for the output layer over here. And for these two inputs, A3 and B3 will be the coefficients or weights respectively, which will be passed on to the final output layer, where we have an activation function that provides us the capability of capturing the non-linearity within the data. And then we finally make the prediction. And using this prediction, we calculate the loss. And this was the entire journey or entire concept behind a forward propagation. Now again, I'm assuming that you have already covered the lecture of activation function from this playlist, and you also have your fundamentals clear around loss function from the machine learning fundamentals. Okay, so from this point, what will be the next step? The next obvious step would be to reduce this loss. And reducing the loss means nothing but the predicted values should be very close to the actual values. That's it. So if you have a data set like this, let's say like this, then instead of having a solution like this straight line, your straight line should work like this, very close to the actual data points. And this is something what we mean when we are saying minimizing the loss. Now let's try to understand that how do we actually minimize this loss. By the way, whatever we are discussing within this lecture, anything about forward or backward propagation, you won't be doing any of these things manually by yourself. All of this will be executed by writing one simple line of code. But as a good data scientist or as a good machine learning or deep learning engineer, you should have a proper understanding behind the operations which is being executed in a deep learning neural network. Otherwise, this entire architecture will become like a black box to you, where you are not able to interpret anything or you don't have any understanding around what's actually happening behind the scene. Now coming back to the topic, in order to reduce this loss, we use the basic concept of calculus and we start the back propagation from this point. In case you do not have a basic understanding around calculus, then please consider checking out the Calculus 1 video tutorial which I have uploaded within this channel. Within 20 to 30 minutes, you will be able to gain a very strong understanding around the calculus fundamentals which is required before studying topics like gradient descent or back propagation. Still, I will try to give you a basic explanation over here so that your learning doesn't get interrupted. So in the field of machine learning or deep learning, lot of times you will hear something like this, where you will be said y is a function of x. And I was very confused when I heard it for the first time. So I was watching a random tutorial and within that lecture, the guy said y is the function of x. And at that point of time, I really got very confused with this simple thing. So just to make sure this doesn't happen with you as well, let me simplify this for you. So let's consider a graph like this. So this is x-axis and this is y-axis. And going by the progression, you can understand when the value on the x-axis is 1, the actual value on y-axis is 2. Similarly, when the input value on the x-axis is 2, the output will be 4 on the y-axis. And again, when the input value is 3, the value on the y-axis will be 6. So going by this particular straight line, we can understand that y has some relation with x. Along with the progress with the input value, the output value on the y-axis is progressing at a certain direction. And this is an example where we can say that y is a function of x, where y is the dependent variable that relies on the input of x. And over here, let's say we need to understand that how the value of y changes with respect to the value of x. That can be defined as this, dy by dx. That will tell us that how a small change within the input value of x will bring a change within the output value of y. And this is the same idea that we are going to apply here to understand that how do we get the loss decreased by bringing some changes to the parameters on which our prediction is dependent. Now think carefully. In order to get this loss reduced, where exactly it is dependent initially? It is dependent on this value of y hat. So we can say that we want to check how the value of loss is changing with respect to a change within the value of y hat. So the next step within the back propagation would be how the value of y hat is changing. Where exactly it is dependent? It is dependent on the output of this particular perceptron. So let's consider the output on this perceptron as Z3. And what will be the equation of Z3? Let's start by the inputs of this layer. So Z1 and Z2 are the inputs here, and A3 and B3 are their respective coefficients. So we can write Z1 multiplied by A3 plus Z2 multiplied by B3 plus let's consider a bias term C3. So in a nutshell, what we are saying is we can bring some changes with the prediction by bringing some changes on Z3 because Y hat is directly dependent on Z3. You can see here. Now let's take the next step with our back propagation, and we need to understand that how do we bring changes with the value of Z3. Where exactly it is dependent? So it is dependent on four factors. First were these two coefficient values and then these two input values. So it is going to have four dependent factors. I'm going to write them down over here. First will be dz3 divided by dA3. Second will be dz3 divided by dB3. Third will be dz3 divided by dz1. And fourth will be dz3 divided by dz2. And similarly, proceeding ahead with our back propagation, these two values z1 and z2 are dependent on these four coefficient values. So what does this entire thing is indicating to? Let me erase all this and then I'll try to explain. Within this particular neural network that we are using here for demonstration purpose, let's count the number of weights that we have here. So we have 1, 2, 3, 4, 5 and 6. We also have two biases, which is this one 7 and this one 8, which means for all these 8 coefficients, we need to adjust the values in such a way that we get the minimum loss, because ultimately these are the 8 coefficients which are actually deciding the final prediction, which is giving us the loss, which means if we are able to find out a way to reach the best values for all these coefficients, then we will be able to reach the best performance for the model that we are trying to build. And moreover, this is the entire process of back propagation. After calculating the loss at this point, we go back within the neural network and we try to adjust the coefficient values in such a way that the predicted value at this point becomes really close to the actual value. And when this particular thing happens, we will be able to achieve the minimum loss. So instead of trying to adjust the values for all these 8 coefficients, let's try to understand that what will be the equation when we are adjusting the value for, let's say, this particular weight, A1. Okay, so we will traverse back from this particular point to this coefficient in order to adjust the value for A1. So let me quickly clean all this. So the first thing that we will calculate will be dl by dy hat, because loss is directly dependent over here on the predicted value. Then dy hat is dependent over here on the output of the final layer. So I will write dy hat divided by dz3 multiplied by, so where exactly this z3 output is dependent, since we are trying to reach over here at this point to adjust the value, we are going to take this particular route, A3, then Z1 and then A1. So I will write dz3 divided by dA3, which is this point, multiplied by dA3 divided by dz1, because A3 is dependent on here, the input value Z1, multiplied by dz1 divided by dA1, finally at this point. And applying the chain rule here, these will cancel out each other. So this goes off, then we cancel out this and then this. And we will finally get that how the loss is changing by bringing a small change within the parameter A1. This is the entire funda of back propagation. And I have shown this thing to you only for one particular coefficient, which is A1. So if I clean it quickly, the way we did it for A1 to bring the loss to minimum by using this particular chain rule, exactly the same way we will also adjust the value of A2, B1, B2, A3, B3, C1 and C2. This is the entire agenda of back propagation, just to understand that how bringing a change within these coefficient values can lead a change, or you can say decrease, with respect to this particular loss. And at this point of time, you might have only one question in your mind, that okay, we understood that adjusting the value of A1 will bring a change in the value of our loss. But how do we actually understand that that how much change we need to make with this value of a1. So let's say initially the value of a1 is 0.3 and the best value will be 0.67. So how do we understand that how large or small step we need to take in order to reach this point? A lot of you will already know the answer. This is being decided or happens completely with the help of algorithms like gradient descent. So in case you do not have much clarity around this topic, you can check it out from the machine learning playlist that we have covered recently. And also within this playlist of deep learning, soon I will be covering a dedicated lecture on optimizers, where I will again cover the topics like gradient descent, mini batch gradient descent, stochastic gradient descent, and all the other optimizers. Those are widely used within the field of deep learning. So do not worry about that. We will be covering everything over here. And please do consider dropping a like below to support my work. I've been working really hard to create these tutorials. Also consider subscribing if you are not yet subscribed, and press the bell icon to get notified every time I'm uploading a new lecture. So that was it for today. Thank you very much for watching till the end, and you have a nice day ahead.